have everybody. So I sent you a paper on yesterday to look at. So we're going to kind of talk about that. Well, I sent you a more summary than the actual paper, but I found the paper and we're going to discuss it today. So let me just get your thoughts on what you thought about the paper itself and uh, what you thought about the technique that they were employing.
So is this I guess you say implementation being used to basically improve the testing with method groups?
Well, not necessarily improve the testing, but actually improve the drugs themselves.
Huh.
You know, they kind of talked about that, about what adding a methyl group can do. Like, what's some of the things that what's one of the major issues that they felt like that adding that methyl group in could address. Anybody remember that part?
I remember they mentioned something about it making it more potent and
Yeah,
more stable as well.
yeah, more stable, so it
Mhm.
persists longer in the body.
Okay.
Yeah.
Because I know they were talking about basically, well, like you said, with the locations of the different acid nitrogen and stuff like that, and
Mhm.
how that affects everything. So
Yeah, so let me pull up the actual paper itself, and then we're gonna kind of walk through it because I didn't get a chance to actually read the paper. I read the summary, but we can look at the paper now. I thought that was pretty cool though. There's just the idea of uh, being able to actually do that, man. I thought that was cool. Let's see. Let me see if I can open it. Then I'll share it. I thought that was actually very cool, and the fact that it just spoke to a lot of things, especially the persistence of that uh, the grad student to just keep moving and keep testing until he found something. Sometimes
mhm.
they can work for you or against you. Sometimes you could be spinning your wheels and you're not gonna get to the bottom of the problem that you're looking at. I had that happen to me as a grad student. Uh, I had a project I was working on. I had several projects that I worked on that were like that. You just end up spinning your wheels and you just don't get anything out of it. You got to know when to cut the cord. Then on the flip side of it, you know, if you cut the cord too soon, that which I've had happen to me, you cut it too soon, then somebody else can come in and make a discovery that you could have made, but you gave up on the project too soon. So it's like it's that old song, The Gambler. Know when to hold them, know when to fold them, and know when to walk away, and know when to run. Like you have to really have like you have to really use some discernment when you're dealing with certain types of projects. Because I read about how the advisor told him that this has very little chance of working, and the student, but the advisor also gave the student the leeway to keep pushing to see what would happen, and then boom, he found this what they call the magic methyl effect. Any other thoughts on it? I just thought it was a really intriguing idea.
So what's the effect of the blue light on those groups?
That's a good question. So again, one of the things that the little summary talked about was the fact that the only way you can get carbon hydrogen bonds activated is you got to energize them. So the blue light is high energy light.
Okay.
It's very high energy, short wavelength, high frequency light, and so that's really in order to do radical reactions, you're either going to do one or two things. You're either going to add in an initiator like a catalyst,
Catalyst. Yeah.
or you're going to shine light on it. And shining light on it, especially UV light, has been the traditional way to get a radical reaction to go. Um, so yeah, you have to have some type of extra energy. You're not just gonna cleave a CH bond homolytically without some
Mhm.
energy being added to that system.
Okay.
Yep. So let's see what they did. Um, so this was the goal: synthesis and structural modification of bioactive molecules, which is what their goal was. Right? They wanted to take molecules that were already biologically active. In the case of either drugs that were already on the market or drugs that, and that was another part of that too, where they talked about taking drug candidates that fizzled out and applying this method to those candidates that fizzled out, just to see if they can make them more viable as drug candidates. Right. So even in the abstract, it talks about, it kind of summarizes everything. Right. And they also had to use a metal catalyst. They use, I think, a nickel catalyst. Um, So, and they use peroxides as the initiators. So, visible light initiated triplet energy transfer promotes homolysis of the OO bond and ditert butyl and dicumyl peroxide under mild conditions. So, that's your initiation part right there. And the alkoxy radicals undergo divergent reactivity, either hydrogen atom transfer from a CH bond or the generation of a methyl radical via beta methyl scission. Right. So, those are your two methods for cleaving the carbon hydrogen bond homolytically. And they also talk about the relative rates of these steps may be tuned by varying the reaction conditions or peroxide substituents to optimize the yield of methylated product arising from nickel mediated. So here we go again with this cross coupling, right? The only difference is they are using uh, radicals instead of, is a radical process instead of a polar process. But the end result is a coupling reaction, which we've already talked about. And these are the coupling reactions are very powerful methods for making carbon-carbon bonds. Um, so let's see what they have here. Let me see what their first table is. Well, they don't have it, but we can go up here and look. Right. So this is one of the drugs. I'm assuming this is one of the drugs that they looked at, and then at this position there was either a hydrogen or a methyl, and you can see right here they said that it's 480 times more potent by changing that hydrogen to a methyl. That's amazing. It's good and bad too, because if it's more potent, I wonder if the drug also exhibits more side effects, which I have to read further to see if they talk about that. Uh, and then right here, uh, a prepient is nausea prevention drug. Right here, this is where they change the methyl, the hydrogen to a methyl group. All right, and again, they they claim increased or improved pharmacokinetics with the methyl group. And what that means is the pharmacokinetic part is the breakdown, right? The metabolism of the drug in the body, right? And so obviously it's metabolizes better with a methyl group than with the hydrogen. And ibuprofen here, you can see we take this all the time, right? It's an anti-inflammatory. It's the racemic mixture too of it. Both isomers work just as well, binding to those pain receptors or inflammation receptors. And it says that here that is non-hepatotoxic with methyl. That's a powerful discovery right there, because one of the drawbacks of taking ibuprofen is that it causes liver damage over time. Like if you take it continually over time, that it can damage your liver. That's what they're talking about here. That is non-hepatotoxic. So that's pretty cool. Um, so here, this is just a basic drug scaffold backbone, and then they're showing that they
Dr.
can.
Russ,
Go ahead. Go ahead.
I don't know if it's just me, but I can't see.
Hmm.
I can't see it either.
I've been talking all this time, and y'all ain't just not saying so. God dog it. Oh look. Let me see. I thought I had shared the screen. What about now?
Yes.
Okay, my bad. That's gonna be a whole section of the recording with me talking, and it's gonna be blank, just a black screen.
Well, at first I was gonna say something, but I thought you were just giving like a little overview and then gonna pop it up.
Nah, nah, my bad. I apologize for that. But here are the drugs right here. This is the first one I was talking about, orexin, and with the methyl group, it's 480 times more potent. And this drug right here, aprepiant, is better metabolized with a methyl group in the place of a hydrogen. And then with ibuprofen, same thing, non-hepatotoxic, so no liver damage from the methyl substituted ibuprofen. Which, I mean, again, that's a pretty amazing accomplishment. And to be able to test that and prove it that's a pretty major accomplishment right there. So right here is like the backbone of a drug. No drug in particular, but this is a pretty ubiquitous functional group right here that's found in a lot of drugs. So I'm assuming that's why they took this and used it. But you can see that they're able to methylate that position without the loss of that stereochemistry. Um, let's see. So this is the peroxide, dietert peroxide, and let me see. Yeah. Okay. So this is the methyl scission reaction right here, where they reacted that with acetone, and then they reacted it with terbutanol, and they did a proton transfer or hydrogen transfer, basically uh, like in the propagation step where you do abstraction of a hydrogen radical. So that's what is happening here. And so then the nickel part comes in where the methyl scission species, which is here, and then the abstraction species here couple, right? So nickel is like the organizing element. I think they said in the overview paper that um, they needed some way to organize the reaction because the radicals are. It, if you ever do chemistry with radicals, you'll find out right away that they're not very stable. They're highly reactive, and it's hard to control those reactions. So the nickel, in this case, is your stabilizing, your controlling element to bring both pieces together. So that's the coupling part that happens. Um, let's look at the table here, and I'll send this paper to you, by the way. Uh, so here's again the peroxide. They treat it with 400 to 470 nanometer light, and this is the hydroxyl radical that they get that goes in and um, does your either abstraction or your scission, right? And you can see right here it says that you get a mixture of abstraction products without the nickel. So with iridium, uh, you get a mixture of abstraction product. And that's one of the problems with radicals is that once you make that radical, man, it's hard, very hard to control the reactivity. So you can imagine this pairing up with itself in a disproportionation type reaction, or pairing up with some other radical, or even pairing up with the hydroxyl radical in termination. So it's very difficult to control that. So here is again they're looking at the beta scission reaction and comparing, like they're trying to optimize it. So get the right photosensitizer, the right wavelength, the right temperature, all of that. So you can see here what they like beta scission versus hydrogen abstraction or hydrogen atom transfer, right? And depending on the conditions. So at 100 degrees with no light, right? This is the ratio. And at 75, at 50, and at 25, you can see that the at room temperature, the abstraction predominates. And then at 50, well, from 100 to 50, you can see that the beta scission predominates, right? So they looked at temperature, concentration, uh, solvent, as well as the type of peroxide, right? And you can see right here The diethyl peroxide is here in blue, and then you can see the ratio of beta scission to abstraction, and then the other peroxide here, you can see the ratio of beta scission to abstraction. So that's how they were able to optimize the reaction, find out what the right which solvent to use, find out which peroxide to use, what concentration, and what temperature. So once you get the optimal conditions, then that's when those are the conditions that you want to do every reaction under. It doesn't matter what the substrates are. So that's what brings them here, right? So you have your substrate here, your peroxide, and then nickel chloride, nickel 2 chloride, uh, and then you add in 1 mole% of that iridium species that's up here. You can see that right here. So I wonder if the iridium plays a role, like a transmetallation role. It doesn't look like it in the mechanism. But like before we were talking about coupling, a lot of those coupling reactions involve like a transmetallation step where you'll have something on one metal that gets transferred to a second metal, but I don't see that here in their proposed catalytic cycle. Yeah, okay, so no nickel, less than 10%, 4 more% of nickel, 60% yield, which is great. Look at the conditions. 25 degrees Celsius. Uh and and so when you have something like this, these mild conditions like this, that's really conducive to like a really broad range of applications. I mean, you're doing this at room temperature, very low catalyst loading, 4% nickel, 1% of that iridium species with under UV light. Uh, that's excellent. Those are excellent conditions. And then yeah, that's pretty cool. And then here's the proposed catalytic cycle. First, you get your abstraction, and then add in your beta scission uh, substrate, and then the nickel is the organizing element for both of those. So you do beta scission, you have your methyl here, and then you couple those two pieces together to give you your product. All right. Um, let me show you how another idea right quick, and then we'll go back to this paper because I want to give you an idea of when you're talking about like drug testing and developing drugs, it's not a one-off type of deal, right? It's a lot of times what a lab is using is what's called combinatorial screening. Let me see if I'll find that because I have a little I have a couple of slides on that actually. So let me find it. Uh-oh, wrong folder. That's just kind of a way to think about it. If you really wanted to optimize a reaction or optimize something quickly, this is a way to do it. To do like a combinatorial screening, and that's what they're not doing. Again, one reaction at a time in a lab that's a drug discovery lab. They're doing hundreds of reactions at a time, and this is even amenable to like microwave assisted synthesis. You can take that plate. If you're doing microwave synthesis, take the plate, put it in a microwave because there's microwave uh, assisted reactions as well. So it's just something to think about. So let's go back to this paper. Where did I have it? I don't want to share it. All right. Can y'all see that paper again?
Yes, sir.
All right. All right. So they also like studied the mechanism of the reaction. They studied the role of nickel, which is here in this diagram D, showing how like nickel actually assists in the reaction. And you can see right here, nickel is actually going to deliver the methyl group. So unlike a typical coupling reaction where the methyl group would be on one metal, and then the R group would be on a different metal, and then the two metals would do transmetallation and swap a ligand out so that both groups will end up on one of those metals. It's a little bit different here. You can see right here the nickel is your methyl delivery substrate, and then it just couples with the R group, right? So it's not a traditional coupling, but it's still a coupling nonetheless because you're bringing two carbon containing species together. Um, and this is a pretty awesome paper. And then you can see their kinetic experiments down here. They're looking for gas evolution, methane or ethane gas, which is right here for this mechanistic experiment. That's what they're looking for, right? So they're looking for either methane or ethane gas. And let me see, what does it say there for? Where is A? So A is favored with no nickel and no abstraction substrate. It says A is so methane is favored. This pathway to form methane is favored, and then here with nickel and no substrate, ethane is favored, which makes sense, right? Because if you don't have the abstraction substrate, then you could imagine if you got two methyls in here and one of them is on that nickel and the other one is a free methyl, then it's just going to couple with the other methyl group. So that's this is a pretty a pretty smart experiment to do to look for the evolution of ethane. And then with nickel and with that's awesome, with the abstraction substrate, then you get the product that's favored. So B plus C. So a little bit of that, and then a little bit of the coupling. 1.1 to uh, 4.7 to 2.2. That's the ratio. So you see the coupling. You also see the ethane formation and a little bit of methane formation. That's pretty cool. That's a really, really smart mechanistic experiment and very well designed. Um, so let's see what they did. Let's see what the scope is. So now they got all of the parameters worked out, and you can see right away. When I was reading this, the first thing I thought was that this student should patent this process because drug companies everywhere are going to be trying to use this to uh, increase their productivity and increase the potency of their drugs. I would have patented this thing. I hope they filed a patent before they published it because this is like revolutionary technology right here. Um, yeah, I definitely would have filed a patent before I published it. And then look at the scope, right? Look at the scope of substrates.
Mhm.
You got a whole page of different types of substrates that you can apply this to.
All right, yeah, that's interesting.
59% yield, 46%, 38%. Let me see what the highest yield is. Um, like they got one here, 61% yield, 61%. So it looks like 61% is the highest yield, but that's still good though. Uh, even if you're working on a gram scale, that's excellent. Wow. And then here are your ligands, and then the peroxides, and then the solvent. Man, that is pretty freaking amazing. Yeah, that's pretty awesome. And then they also account for like the minor regional isomers that you able to, because you know if you methylating that one spot, then there are other spots that are going to be labile too, especially if you got an alkyl chain and you working under these conditions. So here you can get a this is the other regional isomer where you get methyl group here. You can get a methyl group here instead of here on the other regional isomer. But that's really only two substrates that they tried uh, that gave regional isomers. Everything else gave you the same regional chemistry every time. Man. And then they have some late stage drugs down here, which were they were basically these are the drugs that they're looking at and saying these are candidates that have been given up on because maybe they didn't have the right pharmacokinetics, maybe they didn't have the right persistence in the body, so on and so forth. So they're looking at these as late stage candidates, trying to basically salvage them to see if they methylate them, would that make them a better drug? So you can see right here, uh, they are able to methylate here, and then here you can get two regional isomers, um, sitagliptin, which I've never heard of, uh, and then benzofibrate, which you can get two regional isomers, and agomelatine. Let's look those up and see what they are. Agomelatine. Hold up. Oh, it's a mood. It's a mood stabilizer. Mood, anxiety, and cognition. No influence on extracellular. No effect on monoamine uptake. Interesting. So it's a melatonin analog. Okay. Developed under the assumption that abnormal circadian rhythm can contribute to depression. Hmm. Unproven theory, though. Still a good candidate. It activates metalinergic M1 and M2 receptors and inhibits serotogenic 5-HT2C receptors. Okay. Similar to melatonin, it has a longer half life. So you can imagine the half life being even extended even further by methylating it. And I'm pretty sure that was the object of them picking that. Uh, 2.3 hours half life, and it might bind stronger to melatonin receptors. Okay, that's pretty cool. Let's see what the other candidates are. Uh, Nabumetone. Let's see what that is. So that's an anti-inflammatory used to reduce pain, swelling, joint stiffness from arthritis. Non-steroidal, so it's an NSAID, non-steroidal anti-inflammatory drug. Okay, so these are important compounds that they're looking at. Uh, they're not just pulling like something out of their behind, which is I think going to have an application. You need to have one that actually matters. Class of medications, dipeptidyl peptidase inhibitors, increasing amounts of certain. Let's see, where is it? Okay, diet and exercise, lower blood sugar levels, and okay. So this is a diabetes drug. Lower blood sugar levels in adults with type 2 diabetes. That's pretty cool. So I wonder what the effect is of methylating it. I wonder what the effect is of methylating it. And then let's see benzofibrate. Let's see what that is. Y'all can see both screens, right?
Yeah. Well,
When I'm
I can
switching
see.
back and forth to my to enter from the internet to the PDF.
Yes.
All right. Benzofibrate, basalip, fibrate drug, lipid lowering agent to treat hyper. So it's a cholesterol drug. Yeah, this paper is very well put together and very well done. I'm not sure what the benefit of this methylation is for benzofibrate, because again, it can have a persistence effect, it can have a potency effect. So it just depends. And then we already looked up agamelotine. Which one? Oh, we didn't look this one up. Glyburide. Let's see what that is. Another blood sugar anti-diabetic medication. That's pretty cool. Um, yeah, this is very well done, and you see where it ended up in science. You don't get in science unless you come in with the heat. So this has like really broad ramifications for the drug industry. Let's see what else they did. So then they looked at controlling site selectivity because remember we just talked about having regel isomers. So let me see what they did. Hmm. So this is to kind of control that regel selectivity. 60%, 12%. What did they change? They added a Bronsted acid here. Oh wow, they've totally flipped the selectivity. Do you see that? So here they added in a Bronsted acid in addition to the other reaction conditions. And up here without it, 60%, you get 60% of this, 12% of this. Down here, the selectivity totally flips, right? So that wouldn't necessarily be regiochemistry. That would be chemoselectivity. That would be saying I can take two substrates and favor one of them over the other, right? And favor one of them being more reactive than the other. So here, yeah, they've added a Bronsted acid. Looks like trifluoroacetic acid. Yeah, and flipped the chemoselectivity. So they made this species more reactive in that case. Wow. And again, they're looking at these amine salts. And the reason is because they're looking at drugs that contain amine salts and seeing if they can modify those drugs, which is hopefully you can see like the progression. So they start out with a concept, an idea, test it, okay, it works. And then you come behind that and say, okay, now I know it works. Now I want to optimize it. I want to find out what conditions are the best conditions to give me the highest yield and highest selectivity. So then you optimize it. Once you optimize it, then that's when you test out the different substrates. So it's always when you're doing method development, it's the same process. You have a concept, you test it, it works. Then you optimize that the reaction conditions to for that concept, and then you test it on different substrates, right? To opt to get to see which substrates work better: electron rich, electron poor, bulky, non-bulky, so on and so forth. Polarized in this case, like a salt, or non-polarized. And that's kind of the progression that you go through when you're doing method development. So this is pretty cool. Um, let's see what that one drug is. Simple set. Let's see what that is. It's a thyroid drug. Hyperparathyroidism. Hmm, interesting. All right. So it looks like this is a. I'm gonna send this. I'll upload this to Blackboard today in the course notes section. But yeah, this is pretty phenomenal. This is a phenomenal discovery, and the scope is just. Now imagine what would have happened if his advisor had it been a hard nose like this will never work. Don't waste your time. Imagine what would have happened. This may have never been discovered with the wrong advisor. So kudos to the advisor as well for giving the student some leeway to try like something new and allow them to test this out. And I think this student actually wrote their dissertation based on this. So that's why it's so thorough. Right? You got a whole. This is basically a dissertation summarized in 7 pages. So that's pretty awesome. Anybody have any questions or comments about that?